In this video, I'm going to talk about Fourier series, which is one of the most powerful and beautiful pieces of mathematics I know, with applications in differential equations, physics, engineering, and many other places. What's the big idea? Well, I want to begin by thinking about the idea of a periodic function. So this is an example of a periodic function. Goes up, goes down, goes up and down. Indeed, this is just the function sine of x multiplied by some constant out the front that we're not going to worry about just yet. And what I mean by a function like sine being periodic, specifically being 2 pi periodic, is that if I take any spot on the graph and I move over 2 pi, it gives the exact same height. So for instance, 2 consecutive peaks are separated by a distance of 2 pi. But wherever you go, if you move over 2 pi, you get to the exact same height. And so we define this as an example of a periodic function, which just means if you take f of t plus the period capital T, you just get back exactly where you started, f of t. Now, while sine and cosine are probably our sort of quintessential examples of periodic functions, there's many others. So for example, consider this periodic function. This is what we call a square wave. It's either 1 or -1, and it alternates back and forth as well. And this square wave also has a period of 2 pi, which means at any spot that you are, you go over 2 pi and you have the exact same height, the exact same function value. Now, if I think about these two different periodic functions that I have, well, the one very loosely could be said to approximate the other. As in, if I put up sine of x and the square wave, the one that goes between 1 and -1, 1 and -1, well, they're kind of alike. For example, the peaks of sine of x sort of are broadly around the places where the function value is 1, and the troughs of sine of x are kind of where that square wave takes the value of -1. So there's a little bit of a sense in which you could say that there's a rough approximation, but it's a pretty bad one. And in fact, let me actually just zoom in here on just one period. Because it's periodic, it doesn't really matter what happens everywhere else, it's just going to be the same thing. So I'm just going to zoom in between 0 and 2 pi specifically. And so my claim here is that sine of x times 4 over pi, don't worry about that constant just yet, we will get there. My claim here is that this is a bad approximation for this function that's 1 and then -1. So how do I do better? Well, if I wanted a better approximation, okay, it depends on where you are, but you kind of want the green curve to move around a little bit. Some spots, the green curve should be a little higher if it wants to approximate the square wave, and at other spots it should be a little bit lower. So how do I adjust sine of x to be a better approximation to my discontinuous function, my square wave? Well, the idea is as follows. What if I take another sine term? This is the sine term, which is the same 4 over pi. Again, let's ignore that. But this time, it's sine of 3 times x divided out by 3. And there's two 3's here, and they're both important. The fact that it's sine of 3x here means that it's oscillating up and down much faster. And indeed, it's oscillating in quite an important way, because, for example, if I look at the highest value of the green sine of x, that corresponds to the lowest value of sine of 3x. So you can kind of imagine if you added these two things together, there'd be sort of an appropriate cancellation. And then the fact that there's a 1/3 out the front means that this thing that I'm introducing has a much smaller amplitude than the original. Okay, if I add these together, here's what you get. So 4 over pi out the front of sine of x plus 1/3 sine of 3x is this function. I think it's a better approximation. Still not perfect. Still definitely a difference between the green and the yellow, but better. And indeed, we can keep on doing this. Let me add another sine term, sine of 5x. It oscillates even faster. But it still sort of makes sense here because, for example, a little trough in the green curve is kind of aligned with a peak in this new curve, this sine 5x curve. So if I add them together, well, I get yet again a better approximation. And this is the idea of a Fourier series. I'm going to keep on adding sine terms together like this. I could add a few more, or I could add a few more again. And what this now is looking is pretty good. This is a pretty good continuous approximation to the original discontinuous function. This, by the way, is the sum, well, there's a 4 over pi out the front. Again, we're going to ignore that for now. But it's a sum of sine nx divided by n, where n is 1, 3, 5, all the odd numbers. I stopped programming it after 19, but You could keep on going. You could write 1,000,000 terms or 1,000,000,000,000 terms, or take the limit as the number of terms went to infinity of this. And that is the big idea of a Fourier series. It's taking a function and adding up a whole bunch of trigonometric terms of different frequencies. Two sort of qualitative features here that I'm just going to point out, maybe we'll come back later to them. The first is that this sum of sine terms, all those terms are continuous, is continuous as well. But at the discontinuity, notice that it goes sort of right through the midpoint. As in, the square wave was 1 and then -1, and so 0 is the midpoint. And so my sum of sines actually went right through 0 at the value of pi, at the plot spot where this discontinuity occurs. That's kind of interesting. And another little kind of interesting phenomenon that I just sort of want to identify is referred to as Gibbs phenomenon. And this refers to the fact that the approximation was pretty good at a number like pi over 2 or 3 pi over 2. But at the discontinuity, it kind of jumped up a little bit. So this sort of overshooting right around the discontinuity, that's referred to as Gibbs phenomenon. And that's a common issue that happens with Fourier series. They're really good approximations away from a particular discontinuity, but there's a little bit of a jumping around, going around near the discontinuity, which you might expect. Now, here we've been using sine terms to approximate our function. Well, one of the big advantages of using sine terms to approximate a function is that sine is periodic. And so if I now zoom out, I get this larger picture here. So I can imagine a square wave that's 1, -1, 1, -1, and so on. Kind of like you're flipping a switch on, and then you flip a switch off, and then you flip a switch on, and you flip a switch off. That happens all the time in electrical engineering, just for example. And then the fact that I've managed to have this good approximation from 0 to 2 pi, because everything here is periodic, it means I have a good approximation everywhere. And that is one of the biggest strengths of taking a function and approximating it by a sum of trigonometric terms. Okay, that's the big idea, but now let me say it a little bit more precisely. So what I'm going to talk about is some function f of t that has period 2 pi. Then what I'm trying to do is approximate this f of t by trigonometric terms. And specifically what I'm going to say is it's going to be two different sums. Well, first of all, there's a constant value. This is a naught. And for reasons we'll get into a little bit later, it's conventional to call it a naught divided by 2. But then I have a sum of cosine terms, all with coefficients an out the front, and for all possible frequencies, integer frequencies from n equal to 1 all the way up to infinity. So cosine of nt. And then likewise, a sum of sine terms with coefficients bn. So for example, in our case, where we had talked about the square wave, and I'd written down, I gave you the answer ahead of time of 4 divided by pi and the sum of all the odd terms, sine of nx divided by n. Well, how do I interpret this? This is basically saying that all of the cosine terms are 0, because there's no sine here. So that's just saying all of the an's are going to be 0, likewise with including a0 being 0. And then for the bn's, well, because my sum only had odd terms, basically it was saying that if the n value was odd, then you put the value of 1 over n. And if the n value was even, you just put 0. So this example that I have was just an example of a Fourier series. We can say this with a bit more generality. We start with a function defined on some interval minus L up to L, kind of like minus pi up to pi in the case of a trigonometric term. I could imagine extending that function periodically on and on and on to other intervals, like the L to 3L interval, and then the 3L to 5L interval, and so on. But its sort of base definition is on minus L to L. And then I have to look for a Fourier series. It's basically the exact same thing. The only difference here is that now I have a stretching factor inside of my cosine and sine terms. It's a pi over L stretching factor. Same exact idea. Okay, so this is all fine, but it leaves me with quite a bit of questions. That is, what we've been doing thus far is saying, look, I want to take a function and I want to approximate it by adding up sine and cosine terms, and that's going to be really good when everything's periodic. But, well, hold on. How did I find the example that I gave you? For example, I just told you what the AN and the BN are. How do you actually find those? I'm going to answer that in the next video. Additionally, I've got the question of, well, hold on. How do I know what type of functions have convergent Fourier series? When do they converge, and do they always converge to the function? Like, what was going on with that weird midpoint I was referring to earlier? We also have to answer that question. And then finally, this Fourier series topic is being brought up in the context of a differential equations course. And so what the heck does all of this have to do with solving differential equations? And so I want to make that connection clear as well.